Okay, so we are wired for storytelling. Our brains are storytelling machines, but unfortunately, computers, especially early computers, were really not designed with that application in mind. When we think about like Babbage's difference engine, which was designed for calculating logarithm tables, and a lot of early computers that were designed for solving things like differential equations. That was a good choice of early applications because humans can solve differential equations, but it takes lots of years of training, and even then we do it slowly and we make a lot of mistakes. So when you see a computer solve a differential equation, you're pretty impressed, right? At least I am. But not so much with storytelling. So telling a story with a computer is hard for at least two reasons. One, stories are really complicated, so they reason about people. They also have to do things like common sense reasoning and natural language processing, which are all very big, complicated, complex problems. And the other big problem is that people are really good at storytelling. I have a 2.5-year-old daughter, and she's already starting to do storytelling with her toys. We're constantly telling and consuming stories all the time. So when you see a computer tell a basic story, we're sort of like not that impressed because anyone can do it, right? Early computers sort of had their detractors too. This is a quote from the diary of Robert Hooke when he was viewing one of the first early mechanical computers. And he said, "I saw Sir S. Moreland's arithmetic engine very silly." So these early mechanical computers, all they could do was add and subtract. And that at the time, they were not doing them faster or better than humans could do it. If you wanted to add and subtract, this was something people could do, and they could do it faster than these machines. But these machines were still a useful predecessor to the really impressive machines that we have today. So I'm sort of hoping that my research is, providing maybe the spiritual equivalent of these very early storytelling machines. Also, it's worth noting that, it's telling a really simple story is perhaps not as exciting as, or at least doesn't seem as impressive as solving something like a differential equation. But because storytelling is so universal, something that everyone does and something that we do all the time, when we finally make real strides on this problem, when computers finally can do storytelling really well, imagine the revolution that's going to bring to human-computer interaction. Imagine how much easier and natural it's going to be to interact with computer systems. Okay, so story generation and interactive storytelling is sort of a small research community right now. It's getting bigger every year. I think it's a really cool place to be. So this is kind of, I guess, how I've distinguished myself in that area. This is a perhaps long and wordy statement about the sort of work that I do. So I research white box, event level, interactive narrative planning algorithms for virtual environments with story spaces too large to map out in advance, but with strong aesthetic or pedagogic constraints on their content. So I want to kind of break this down like into bit by bit here. So the first keyword here is white box. So I generally do not work with machine learning algorithms, which is nothing against machine learning. It's just that when I work on stuff, I really like not only the result that is produced to be something that a human can look at and make sense of, but I like the process to be inspectable as well. I like to be able to pause the algorithm at any moment and sort of open the lid and look at it and be able to make sense of the solution in progress. And I like for each of the steps for making changes to that partial solution to make sense to a human author. And part of this is because a lot of what we choose to model and how we design the algorithms are often inspired by the way that people tell stories. So I like to be able to take insights from storytellers and narratologists and psychologists and use those as inspiration for how the algorithms are going to work. And also because I like to learn about people. Like, I don't really consider it a successful project just because we were able to come up with an algorithm that tells a story. The really good projects are one where you actually learn something interesting about human storytelling in the process. Okay, so I work with event level interactive narratives. So narratives fall on this spectrum in terms of their granularity. So on a lot of the most successful early interactive narratives worked at the scene level granularity. So I have up here Facade, which is a very famous and successful early interactive narrative game. And the sort of atomic unit of story that they are using in Facade is a scene or a beat. So there's like a small, 30-second to 2-minute long experience that has been hand designed by an author, and the algorithm is deciding which of these scenes or beats am I going to present in what order and at what time. And thanks to the revolution in like large language transformers, we're seeing some really interesting work coming out just in the last decade or so for word level granularity, where the AI is actually deciding one word at a time how to compose its output. I think that's a really incredibly ambitious project, and there's a lot of long-term questions there. But the place that I like to work, the place where I think we have the most high impact and sort of nearish term contributions is in the middle, which is event level. So I have up here a screenshot from The Secret of Monkey Island, which was one of my favorite games growing up. I still have very fond memories playing this game with my dad when I was growing up. And so the interface for this game, I'm not sure if you can read it or if you've played this kind of game, but there's like some verbs in the bottom left, and all your interactions with the game are like click on a verb and then click on something in the scene, either in your inventory or in the world. So you can do things like, put on the pot and climb into the cannon and shoot yourself off of the ship onto the island. So in this case, an atomic unit of story content corresponds roughly to like 1 sentence of text. So it's usually like subject, verb, direct object, something like that. So that's the level of granularity that I'm working at. Okay, I work with narrative planning algorithms. I'll talk very briefly about what planning is in a minute. But also when I say planned, I mean that sort of in contrast to emergent narratives. So far, a lot of the most successful interactive storytelling systems have been emergent narratives, where you create an environment and then you create one or probably several or maybe a whole host of intelligent agents, and you sort of wind them up and let them loose. And the idea is that an interesting or useful story will kind of emerge out of this sort of society of agents in this virtual world. And so some of the really successful examples on this end of the spectrum are games like Dwarf Fortress or The Sims, if you've played these sort of games. But the other end of that spectrum is what we would call sort of planned stories. And so that's a story that has been really carefully handcrafted, and in most cases by a human author. So I have some examples like the Walking Dead series by Telltale or the Mass Effect series. These are like, interactive experiences that have been praised for these very carefully handcrafted stories. And so what I'm interested in is working on this end of the spectrum, the planned side of the spectrum, but in generating these stories automatically, or at least where the computer is like a helpful co-creative participant. So I work in virtual environments, and here it's sort of worth noting that our research area in story generation has people coming from sort of 3 broad camps. One of the big ones is film. So a lot of people come at this area from a film background, and the film people are really good at narrative structure and characterization and like story arc and that kind of stuff. But the place where the film background people sort of struggle is releasing that agency to the user, allowing the user to move around and break things in this carefully crafted virtual world and make those interactions meaningful. The other big camp, one of the other big camps, and the one that I'm coming out of, is the game development camp. So the game development people tend to be good about providing these really meaningfully interactive experiences, but sometimes we struggle with getting that good narrative structure and characterization out of it. And there's a third community that's coming in just in the last maybe 1 to 2 decades, really earlier than that, but especially lately, which is the natural language processing community. And they're coming at it because they've been working in the past sort of at the word level, sentence level, maybe the paragraph level, and they're interested in moving into these much larger texts. How do we consider natural language understanding and generation in the sense of a much larger piece? And they're bringing a lot of really cool machine learning expertise with them. Okay, and so I like to work in I want to work in story spaces that are too large to map out in advance. So this is a diagram that GameBeats made of the plot of the Telltale Walking Dead series. And it's showing sort of every choice and every way the story can be different based on your choices. And it's like really impressive. Hopefully, like me, you see this, you say, wow, what a big, complicated story. But you're maybe also struck by the fact that it has all these what we'd call sort of like diamond branches. Like there's a choice to make, and then you get some like immediate feedback. You see an immediate change in the story world based on your choice, but then we're very quickly routed back to this kind of central spine. And that, makes sense. This is a survival mechanism that human authors of interactive stories have to use, because with every true branch in your story, the number of possible like endings and outcomes multiplies exponentially. So there's a huge authoring effort into creating these stories, and so we tend to rely on these sort of tricks to get a lot of content out of. I'm not going to say little authoring, because a ton of authoring went into this, but to make the content that we create very reusable. This is one of the plot diagrams from Bandersnatch, this sort of interactive episode of Black Mirror that a lot of people really enjoyed. And this is kind of a broader graph. You can see, more branching and interaction between these stories. But this was still an incredible undertaking. It took tons and tons of writing and filming to create what was otherwise what felt like kind of a short episode of Black Mirror, depending on how many times you rewatched it. So there's a massive authoring effort that goes into creating these spaces. And what I'm interested in is creating the algorithms that can generate stories on the fly, so that we are no longer limited in scope by the size of stories that someone can plan out in advance. This is a book called Paper Pong by Richard Moore, and you can actually buy a physical copy of this. And it's a choose your own adventure book where you play Pong. So every page is like a screen of the game Pong, and there's like, so for example, here it says, if you want to move the paddle up, turn to page 114. If you want to move the paddle down, turn to page 117. And we say, okay, well, I want to turn it up. So then you turn to page 114, and here's what it is. So it's a choose your own adventure book where you're playing Pong. And the reason that this book was created as kind of a rhetorical artifact to point out the absurdity of doing something like Pong in this kind of system, right? Like Pong, one of the very first video games, had this really nice procedural, I hesitate to call it physics, but it was physics in the world of Pong, which just had this idea of like, okay, the ball sort of continues in the direction that it's going until it hits something and then it bounces off. And it really made sense, both in terms of, creating the actual electronic artifact, but also in the experience for this to be procedural. But stories aren't like this. Even today, when we create these big, elaborate, interactive stories, we're just doing paper Pong. We're having humans write out the entire story in advance. And really, these things should be procedural. So, what would the equivalent of a physics engine be for story? Those are the kind of questions that we're asking. Okay. And then finally, one of the other things that sort of distinguishes the work that we're doing is we are bound by aesthetic or pedagogic constraints that are handed to us by the author. So in an emergent storytelling system, often any old story will do. That's kind of an exaggeration, really. You design the agents and you design the world such that any story that emerges is interesting. But I'm specifically interested in working in worlds where the author has handed us some constraints that we have to live by. So I'm really interested in making like computer role-playing games feel more like their tabletop role-playing game predecessors, where you have a human storyteller or many storytellers who are sort of guiding this narrative experience. To make the training simulations used by the military and police officers and nurses and firefighters, to make them feel less like virtual shooting ranges and more like the, in-person role-playing exercises that are used to teach like de-escalation tactics and that kind of thing. And then to make intelligent tutoring systems less like these gamified math problems and more like the actual like personal customized attention that you would get from a real human tutor. So my personal goal, the sort of moment where I would sit back in my chair and say, ah, yes, this is it, I've arrived, is when I create a system that surprises me with an interactive story in a domain that I wrote. So basically, when I say domain, I said we're working at the event level. You're basically providing the Lego blocks of a story, and the algorithm is putting those Lego blocks together into a structure. And the moment that I'm going to say, this is it, I've arrived, is when my algorithm tells me a surprising but good story in a domain that I wrote. So it takes all the Lego blocks that I provided and it builds a really interesting and surprising story out of it. And I guess the keyword here is pleasantly, because I've been surprised by the output of my algorithm quite a lot in the last few years, but rarely pleasantly. And that's actually sort of how I'm going to structure the rest of today's talk. So the title is Learning from MIS-SPUN Tales. And that phrase comes from an early paper on story generation in 1977 on a system called Tailspin. And this paper is really interesting because it presents an early storytelling system, but sort of everyone agrees that the most interesting part of this paper is the section on MIS-SPUN tales, where the author gives the output of like some of the really terrible examples that this algorithm was creating. And this wasn't so much a criticism of the system, but it was demonstrating what needed to happen next. And so a lot of my research has been creating a storytelling algorithm, seeing the weird, bad stories that it creates, and using that as guidelines for figuring out where we need to go next. So our story begins with this paper, which was written by the person who would eventually become my graduate advisor, Michael Young. And in this paper, he proposes that AI planning algorithms would be a good basis for a story generation and interactive storytelling system. And AI planning, for anyone who's not a computer scientist or doesn't have a background in AI, you provide it three things. You describe the initial state of the world, and you describe a goal that you want to achieve, and you provide some action templates. So these action templates have preconditions that need to be true before the actions can happen, and effects which change the world in some way. So for example, this is not really a template, this is a specific action here. But someone walks from one place to another place. So in this case, the player walks from their home to the market. And the precondition is, well, for that to happen, the player needs to be at home. And the way that changes the world is, well, the player's not at home anymore, now they're at the market. And you can imagine this like purchase action where like in order to buy the potion, the player needs to be at the market and they need to have money. And now they no longer have money, but maybe now they do have the potion. And so these algorithms are useful for a lot of reasons. They're generative, which is nice. They can generate whole stories, whole cloth, or partially from a partially completed story. They have these really nice formal properties that have been studied by a lot of very brilliant scientists. For example, these planning algorithms are sound, so they're guaranteed to return solutions that work. They're complete, so given enough time and memory, if a solution exists, they will find the solution. Many flavors of these algorithms can work with partial stories, so they can reason about the fact that, well, someone needs to walk from the home to the market and someone needs to buy the potion, but we don't really care who, and we can decide who that's going to be later on. So they can build these stories in sort of partial ways that have some correspondence to the way that people think about stories or think about the authoring process. They also have this nice model of causality. So we can detect when the effect of an earlier action satisfies the precondition of a later action. That allows us to draw a causal link between these actions and reason about causal chains. And causal links and causal chains are really helpful for like operationalizing a lot of storytelling concepts that narratologists have studied. It also allows us to do things like partially ordered stories where we put sort of minimal constraints on which events need to happen in what order. So there are a lot of reasons why planning algorithms are a good basis for storytelling systems. But there are, and this was proposed as a good place to start, and indeed it was a really good place to start, but it was not the place to finish. There are a lot of stories generated by planners that don't make good stories. So here's our first MIS-SPUN tale of the day. So I'm going to try to keep all my examples today in this little small domain that kind of fits on a PowerPoint slide that we've worked with in the past. So imagine there's a crossroads that connects a number of locations. One of them is your home. You're the player over here on the side, and you've got a bag of money. And in the market, there is a merchant who is selling a potion. And in this case, the potion is just the MacGuffin. Like the point of the story is you need to go and get that potion. That's your quest. So here is a story that can happen if you hand off this, you say, here's the initial state, here's where everybody is, here's what items they have. And the goal is that I want the player to have the MacGuffin by the end. Well, here's a story that a classical planner might generate. The merchant walks to your house and gives you the potion. Hey, that's great. That was a really efficient path from the initial state to the goal, and planning algorithms were originally devised for things like robot movement and factory scheduling. And so this is a very planner-like solution to that problem. But it doesn't feel like a good story because we look at that and we say, well, why did the merchant do that? You know, isn't the merchant here to make money? Like, this really doesn't, I don't understand why the merchant's just giving away her inventory. And so a researcher named Mark Rydell came in and worked with Michael Young and said, well, we can add this concept of intention to these planning algorithms. So on top of, and this blue circle represents the space of like all valid plans. So this is like every executable sequence of actions that gets us from the initial state to the goal. And they realized that actually we really are interested in a subset of those sequences where every action that an agent takes can be explained in terms of those agents' goals. So for example, this would be a story that we could tell with an intentional planner. We could tell this with a classical planner too, but this is one that is in that intentional space. So the player walks the market and purchases the potion. Like, that makes sense, right? Because, you know, here's our story and we can say, well, why did the player buy the potion? Because they wanted the potion. Why was the merchant willing to do that? Well, the merchant wanted money. And so every action needs to be either explained because either it achieved the character's goal or it sort of enabled the character to achieve the goal. So why did the player walk to the market? Well, they did it to buy the potion. Why did they go to the crossroads? They did it so they could go to the market. So intentional planning is this idea of it needs to be a valid plan, but it needs to be one where every action is explainable in terms of the character's goals. But there's a problem. Like, this domain is very, very small and simple. We want to spice it up, especially these fictional stories need some conflict to make it interesting, right? So let's imagine that we had a bandit as well. So the other branch off of this crossroads, there's a camp in the forest, and there's a bandit who wants to steal valuable stuff. And we would like to be able to tell this story, right, where you are headed to the market, but on your way you are waylaid by a bandit who steals your money. Like, this would make the quest a little bit more interesting. But we can't tell that story with an intentional planner. And the reason is, if we look at this sequence, so the player walks to the crossroads, the bandit goes to the crossroads, and the bandit steals the money, we can understand these bandit actions in terms of the bandit's goal. Why did the bandit do it? Well, the bandit wants your money. That makes sense. But we can't explain this action. The player has to walk to the crossroads, and the player has no reason to do it. The player doesn't want their money to get stolen, so why are they going to walk to the crossroads? And, you know, we as humans can look at that and say, well, you know, that needs to happen for the story to work out, but that's not good enough anymore. We're working with an intentional planner. We want every action to be explainable in terms of character goals. And so my dissertation work was in solving this conflict problem, where we said, well, actually, we can explain why the player would walk to the crossroads because of what the player intended to do. So they were going to the crossroads because they were hoping to get to the market and buy the potion. And if that had happened, it would really make sense why the player went to the crossroads. And it turns out that isn't what happened. Their plan was not allowed to continue because the bandit came in and caused a conflict. So if you have a computer science background, what this means is we are treating other branches of the search space as meaningful possible worlds that inform the story that actually happened. So the way these planning algorithms work is they are exploring the space of all possible stories, looking for one that meets our like author requirements. And so in the process of coming up with the actual story, we're going to imagine this version of the story where the player got to the market and bought the potion. And the fact that this branch exists tells us that it's okay for the player to walk to the crossroads, even if that doesn't really happen. And so this was an algorithm that we created that we actually won Best Student Paper for this. We were really excited for it. And basically, it is treating the search space of the problem as a map of possible worlds. And that's nice because in traditional AI planning, everything other than the actual solution in the search space is really kind of thrown away as like wasted work. But here, it's not wasted work. Those other ways the story could have gone provide us meaningful examples of other ways the story could have happened. And there's a lot of psychological evidence that people are thinking about the meaning of story events in terms of what would have happened if they didn't happen or if they'd happened a different way. We also were able to bring in some research from fast AI heuristic planning. And so the original intentional problem which was telling the story of Aladdin. They had to visit 1.8 million nodes, and it took over 12 hours to generate that story. We were able to generate a similar story in about 20 milliseconds, visiting only a couple hundred nodes. So we were able to not only add this notion of conflict, but we were able to really speed up the algorithms, which was nice. And this was, for the computer scientists in the audience, it was really interesting because classical planning heuristics are all Markovian, so they assume that the only thing you need to estimate distance to the goal is to know the current state. But that's no longer the case, because you now have to think about, how am I going to get to the goal, but how am I only going to get there via actions that make sense? So you not only have to reason about the cost of getting to the goal, but also the cost of coming up with explanations for all the actions that have happened and are about to happen in the future. And so these fast conflict planning algorithms allowed us to produce a game called the Best Laid Plans. It's not an especially fun game. It's really a research prototype. But this is a game of, you are the hapless goblin minion of this evil wizard, and you've been sent to get the potion, which in this game is a bottle of hair tonic for your sort of skeleton overlord here. And this is the story of how everything goes terribly wrong. So you're on this quest, this seemingly menial quest, but every time you complete it, some character comes and causes a problem. But they have to do it in a way that sort of makes sense for that character. So you go to the market, you buy the potion, and then on your way home, the bandit steals it from you. So then you go back to the market and you steal a sword, hoping to get the potion back from the bandit. But now you've stolen something, so the guard in the market is mad at you, and so on. So it's just sort of intelligent. And the interesting thing about this game was there are no pre-written behaviors for any of the characters. We gave the game the Lego blocks, which is, you can walk from one place to another, you can pick up an item, you can buy an item, that kind of stuff. And the game is building the story out of these events, and it's doing so intelligently, trying to create some interesting conflict. Okay, so basically my contribution for my dissertation work was saying it's not that character goals actually have to be achieved. There just has to exist a sequence of actions that would achieve that character's goal in order to explain it, even if that sequence doesn't really happen. And here's my favorite MIS-SPUN tale that came out of this game. In addition to the merchant and the bandit, there's also a guard who's in the town, like guarding the market. The guard wants to punish criminals. And we wanted to have lots of different ways that you could play this game. And so we decided that the guard was also going to be hungry. And there were a few reasons that was helpful, like maybe you could give your money to the guard and the guard would leave his post to go buy some food, or maybe you could get some food and like poison it and take the guard out of commission. But here's what actually happened. So before you would actually start doing anything in the game, the first thing the guard would do is steal some food. And because the guard was now a criminal, attack himself. So every time the player would arrive in the market, there was just this like guard sprawled out on the ground, dead by his own hand, like clutching a chicken leg in his hand. And you would look at this and wonder, like, what on earth happened? And the reason that was happening was because all of those actions, the guard's actions to steal the food, can be explained in terms of his hunger. And the reason he attacked himself can be explained by his like motivation to, attack criminals. But and actually, the system did sort of represent that as an internal conflict, but it didn't really resolve or reason about it in an interesting way. So what we learned from that MIS-SPUN tale is that actually we need to measure agent utility, not just their goals. So we need a way of specifying that some goals are more important than others. Okay, but there's another problem with the guard. So here's another MIS-SPUN tale. So you walk to the crossroads, the bandit shows up, the bandit steals your money. We're telling our good conflict story, that's nice. And you're thinking, oh, how am I gonna resolve this? Well, instantly the guard shows up and takes out the bandit for you. And this story, it's feeling a little bit better than some of the previous MIS-SPUN tales, but it's still problematic because the guard didn't see that happen. Like the guard was off in the market. How did the guard know that you were in need of assistance? The guard is exhibiting this sort of psychic behavior. And the reason that happens is because these planning algorithms are taking the author's perspective, sort of a God's eye view of the world, which means everybody knows everything that happens all the time. And that's not realistic, right? Characters aren't omniscient. And so what that revealed to us is that there's this really important other space of stories in terms of what actions characters think can happen. So our new hypothesis was that really the interesting stories, the interesting character plans are in this purple area. So a character plan makes sense if the character believes that that sequence of actions could increase their utility. So this allows characters to have wrong beliefs and to miss things, like to not observe actions that happen. And we were really proud of this paper because we took sort of a different approach to evaluating the storytelling system. A lot of previous systems, you would sort of pick one story that your algorithm had generated, and then one control story, and you would have people compare those two stories. But of course, the temptation there is to cherry pick a really good story out of your system and maybe to cherry pick a really bad control. So when we did this evaluation, we actually generated all possible stories of a certain length in this domain, and then we sampled from these different spaces. So we would always pick two stories in the same domain from two different regions of this Venn diagram and have people read them and say which of these is better. And so that experiment demonstrated that stories where characters reason about belief are better, stories where they reason about intention are better, but stories where they reason about both are the best. Okay, we've still got some problems though, more misspun tales. So one of the things that would happen in the most recent game that we built based on this technology is you head to the crossroads, the guard shows up, the guard steals your money, but then the guard continues onto the market because the guard says like, hey, the potion's valuable, I want to go get that too. But of course, as soon as the guard shows up in the market, the guard sort of takes him out. You know, the guard shows up carrying contraband, and that's the end of things for the bandit. And so, you know, it doesn't make sense. Like the bandit needs to realize like, hey, I've got my stuff. I need to not walk into this really dangerous situation where the town guard's going to get me. And what that sort of prompted was there's another dimension to these stories that we need to be thinking about, which is emotion. And this is one of my PhD students who's actually getting ready to graduate now, is reasoning about how we can model emotion. And so even though we weren't calling it this before, we were implicitly modeling these three emotions already. Hope, which was a way to imagine, you know, increasing your utility or achieving your goal. And joy, which was this feeling of, hey, you did it, you achieved your goal, you increased your utility. But it would also be nice to reason about things like fear. Like you need to be able to imagine, you know, your utility going down or somebody thwarting your goal and the corresponding emotions behind that. And we don't plan for fear. We don't intentionally try to bring our fears about, but we do plan for things like relief, which is we create stories where we intentionally want to avoid having our goals thwarted or our utilities lowered. And so reasoning about belief allows us to tell new stories we couldn't tell before, such as this one. Like, let's imagine you had more than one sack of money, and let's imagine the merchant is selling a sword as well as a potion. And so you could go to town and you could buy the potion. Like, this makes sense, right? Your goal is to get the potion. Everything checks out so far. But then you buy the sword, and you might say, well, that didn't make sense according to our previous model, because you don't want the sword, and actually it would be, you know, all things being equal, you'd like to have more money than less money. So why did you buy the sword? But this story still makes sense to people, because you can say, well, I bought the sword because on my way home I don't want to get robbed by the bandit. And so buying that sword can be explained by the emotion of relief. You know, I feared being robbed by the bandit, so I took action to prevent my fears from being realized. And so our current model in the story generation system is saying that really the sweet spot, the believable set of stories, is this purple region. So it's the sequence of actions that a character believes can happen that will lead to triggering a positive emotion. So either achieving their goal or preventing their goals from being thwarted. So story generation algorithms are all well and good, but if you just have a single like one-off story that you want to write, you should probably just hire a person to do that. People are really good at storytelling. There are so many storytellers out there who want to write stories. And the goal is not to replace storytellers with this research. The reason that we're developing the storytelling algorithms is for experience management. The value of a narrative planner is so that we can constantly write and rewrite the story on the fly in an interactive experience. And experience management is its own sort of problem on top of the storytelling algorithm as a component of experience management, but it also leads to some other really interesting problems. So let's imagine this is the state space of the possible stories we could tell. And we're currently in this state here on the left. And these arrows represent actions. The blue ones are actions that we control. So these are actions by the non-player characters. And these green ones are actions taken by the player. And so over here on the right are the possible endings that we could have. And we've determined for whatever aesthetic or pedagogic reasons that these two endings are good ones and this one's bad. And so the most straightforward way to use a narrative planner as an experience manager is just to say, well, would this be a good action for us to take? yeah, that seems fine because there exists a good story. If we take that action, there is still a way to get to a good ending. We asked our narrative planner to write us a story, and this is the story it gave us. Great. Well, the problem is players don't always cooperate with how we think the story is going to go. Maybe the player does this instead. And is it okay for the player to do that? Well, the narrative planner says, yeah, that's fine because there still exists a way to get to the good ending. But again, what if the player doesn't cooperate with that story? What if that's not what they choose to do? What if they try to take this action? They're going to end up in an experience that is, for whatever reason, not one that we are allowed to have. Our author constraints said this is not an acceptable story. And at this point, we're forced to do something called like intervention, which is we basically prevent the player from taking this action because it would lead us to a bad story. And this is a phenomenon that you see called like plot armor. So if you've played games like Skyrim, if you get into a fight with a character who's important to the story, and you win that fight, that character is just going to sort of kneel down and say like, okay, you know, you've defeated me, but I need to stay alive because I'm important for some future part of the story. And in that moment, it sort of breaks the immersion because it disrupts this rule-based experience that we've come to expect. You know, the player expected to be able to take an action, and suddenly we see the invisible hand of the author kind of intervening and preventing that from happening in a way that feels very sort of transparent and immersion breaking. So a good experience manager needs to realize that first action was a bad choice. This is the action we need to take because no matter what the player does, we're going to end up in a good experience. So we built another game using Camelot, which is a tool that we've developed for sort of rapid prototyping these interactive narrative environments. And Camelot is free and open source if anyone wants to go download it and play with it. It's a great way to teach like introductory programming classes. Any programming language that can read and write to the console, you can make a interactive narrative game using Camelot. So anyway, we built several little prototypes that were the successor to Best Laid Plans. One of the things that made Best Laid Plans not a fun game was you had to act out exactly what you wanted to do in advance so that the experience manager could know what you were going to do so that it could thwart your plan. And it was a really tedious experience to say, here's what I want to do, and then the storyteller kind of screwing you up. But we built this one of our Camelot experiences, and we said, well, let's use a story domain that is small enough that we can actually generate that entire plot graph. We can imagine every single possible outcome ever, which means anytime we make a decision, we know all the long-term consequences of that decision. And we were able to do it. We wanted to keep different endings available, allow people to play the game in lots of different ways. We're going to pre-compute all our decisions, but that's really hard. We're basically using the tiny little domain that I've been showing on this PowerPoint slide with like a couple extra features. And how hard was this to do? Well, that graph has over 500 million nodes in it and 1.5 million edges. And the only way we were able to even generate that graph, much less reason about it, was to use a supercomputer with 1.5 terabytes of RAM. And thanks to the Louisiana Optical Networking Initiative for letting us use their fancy supercomputer to do this work. So the lesson here is that even these really tiny, simple storytelling domains get real big, real fast. But the good news is, even in this little domain, we were able to create a really effective experience management experience. Players said that characters felt realistic, they reacted to things that they saw, they tried to accomplish their goals. They felt like their actions had a significant effect on the story, which was great. But we had a sort of a misspun tale that arose not in the game, but in the real world here. We were comparing our game to a control, and in the control, the non-player characters just act randomly. They'd always just sort of pick a random action and take it. And it turns out that people actually liked the random version also. Thankfully, they liked our version better, but they still liked the random version. And people who played that version told me all these funny little stories. They're like, yeah, I walked the market and the bandit and the guard weren't doing anything. And I left and I came back and now the merchant was attacking the guard. And I figured, you know, they must've been lovers. And when I left, they had some fight off screen and now they've had a falling out or something. It's like, no, they were just doing random actions. But the lesson here was that people try to make a story out of anything. If you show people a sequence of events, they will jump through incredible mental hoops to make a story out of it. So this has provided an interesting challenge for us in our research for coming up with effective controls to compare our work against, because we've got to control for that desire of people to make stories out of anything they see. Okay, so here's one more misspun tale from the actual games themselves. In our experience management game, we had something like this where the merchant would come to your house, and thankfully the merchant doesn't give you the potion because we're reasoning about intentionality. The merchant still wants you to buy it, and it's like, okay, this is fine. The merchant's being proactive. They're coming to you rather than waiting for you to come to them. But what if you don't want to do it that way? So you say, no thanks, and you go to the crossroads. Well, the merchant follows you because they're still hoping to sell you that potion. You say, oh, that's okay, I'm going to go to the market. Well, the merchant follows you because they're still hoping to sell you that potion. And you actually end up with this like posse of non-player characters like following you around everywhere in the game because they're all sort of hoping for this one particular interaction. Like they all want to sell you something or get information from you or something like that. And that really feels bad. And it feels bad because we are not realizing what the player is trying to do. The player has sort of told us, no, I don't want to buy the potion, but we kind of haven't realized that and responded to it. And the reason for that is we're not recognizing what the player wants to do. This was the problem with best laid plans. We weren't recognizing the player's plan. We were just making them tell us what their plan was. It would be really nice if we could just infer what their plan was. And it turns out we can do this. So up until now, we've been working with planning algorithms that reason about belief and intention, which says if you know what agents believe and what they want, what should agents do? Well, we can use these same algorithms to solve the reverse problem, which is if we know what an agent did, what beliefs and intentions probably explain their actions. And I'm not going to go into detail to how this works, but basically you look at the actions that happened, you look at some candidate beliefs and intentions, and you figure out how easy it is to fill in the missing pieces with the planning algorithm. The easier it is to fill in the missing pieces, the more likely those intentions and beliefs are to be the right ones. And we actually did this work for a lab that supports the intelligence community for helping intelligence analysts like imagine why certain global events are happening. They see global events, they're trying to imagine like why was someone doing this? What caused them to? So this was developed as a tool to help people make sense of the events that they see. Okay, so one more misspun tale here. You've gone to the market, you've bought both a potion and a sword. So this is good. The bandit can't rob you. The bandit can still kill you and take the potion, but at least they can't rob you. So you've avoided some possible conflicts, which is nice. And then you're on your way home, and then the bandit shows up, and then the bandit just stands there. So the bandit runs out of the camp, runs right up to you, draws their sword, and then does nothing. They just stand there. And this is something that happened in our most recent version of the game. We said, what's happening? Why is the bandit running up to you, drawing their sword, and then just standing there? And the reason was because one of the goals of our experience manager was to keep different endings available. We want to keep the ending where you made it home with the potion available. And when the bandit kills you to take the potion, that cuts off one of the endings. And so the experience manager was saying like, nope, bandit, you can't attack because that's going to cut off endings. But that was creating this problematic experience because when you see the bandit walk up to you, when you see the bandit draw her sword, it creates this expectation that the bandit's going to do something else. And then when the bandit doesn't follow through, that sort of breaks the experience. So we've also done some work on integrating models from cognitive science into these planning algorithms to try to model what players remember and expect. There's several decades of work on something that's called the event indexing situation model, which says that as we look at events, we store those in short-term memory based on who was involved, where it happened, when it happened, why it happened, and how it happened. And I'm not going to go into the details on how we use this model, but basically, if we reason about those things, not only can we reason about what events people remember more easily, but we can also reason about what choices they're more likely to make. People make choices that make their past actions more salient. And also, we discovered that we can influence the choices people make. We can engineer the content of our story to encourage people to make certain choices. But here again, we had some real life misspun tales. The first version of this experiment, we just told the story and then we gave them one choice at the end, and we didn't get significant results there. And credit to Rachel Farrell, one of my PhD students, for basically rerunning 4 different versions of this experiment until we got good results, because we learned really interesting stuff out of every version of this. Turns out that no, you have to allow players to make decisions, but not just any decisions. Those decisions have to be related to the meaningful choices they're going to make, and you have to give them the choice to make sort of bad versions of those decisions or versions that would lead to different stories. Only under these conditions can we influence what choices people are going to make with the content in our story. So we thought that was really interesting. What are we doing now? We're applying this work for some virtual reality de-escalation training simulations. I sort of like to think of this as a non-shooting range. Like a lot of the previous work for VR training has basically been a VR shooting range. We're interested in creating the VR equivalent of like a role-playing exercise to hopefully teach people how to get to situations where you don't have to shoot. And we're working with the UK Police Department with their de-escalation training team, who has the people who are in charge of training officers to de-escalate situations. So we're really happy to be working with such excellent subject matter experts. And this is sort of the closest that we've come to, achieving something like the Star Trek holodeck. Like it really feels real. We've got an intelligent algorithm that's generating the story on the fly, and it's generating it in such a way to teach these de-escalation principles, to encourage right behavior and to reward right behavior and discourage wrong behavior. So I'm a little bit over time. Just very quick, the sort of takeaways from this talk. We learned a lot from failure. In fact, the times that we failed, they taught us more than our successes. Also, storytelling is really big. These interactive spaces get really big, really fast, and planning is expensive. We know it can be done because people do it all the time. And appearing realistic is easier than actually being realistic. So there are a lot of shortcuts you can take when all you need is for your agents to appear realistic, but not actually be realistic. Also, one of the big challenges is thinking backwards and forwards. We need to think backwards from the goal to ensure story structure, but we need to simulate forwards so that we don't get the shy bandit problem where the bandit just walks up to you, draws the sword, and does nothing. And storytelling is non-Markovian. It's not enough to know the current state. People think of stories as a sequence of actions. You have to think about those past sequence of actions to decide what your future actions are going to be. And stories come naturally to people. This is both the reason our work has been successful and the biggest challenge that we've encountered, that people try to make a story out of anything they see. And so it's good to know we have to be careful not to cherry pick the good examples from our system or the bad examples from other systems when we're doing our evaluation. And of course, the real proof of pudding comes when we actually put our algorithms to work in a real interactive artifact. And then my last sort of closing remark is that we are still in the cave painting phase of interactive narrative. We are still in the very early stages of generating this. So I hope you'll come join us and do some cool interactive narrative work, because eventually we're going to get to writing Shakespeare. Right now, we're still doing cave painting. Many thanks to the different organizations that funded this research and all my incredible graduate students and co-authors and mentors for making this work happen.